Hello, everybody. Welcome back. I'm now happy to introduce you to the next talk given by Tim Ruhe from the TU Dortmund University. He is a postdoc at the chair of Astroparticle physics and also the PI of the C3 project of the CRC. And with his over more than 10 years experience of with astroparticle physics experiments, especially IceCube. He's the perfect speaker for the next topic, of course. And he will give us a talk about machine learning applications in astroparticle physics. The stage is yours.
Yeah, thank you for the introduction. I'm happy to be here. And so one disclaimer, when I accepted the invitation, I said, yes, of course, I can talk about machine learning applications as to particle physics in 90 minutes. Turns out it's a way too wide topic because it has become sort of a standard tool and many experiments utilize it. So I tried to focus this, which means I focus it on a very particular experiment. And this is the experiment I work on myself, which is IceCube. So, but the basic point is that all the things I'm going to tell you are applicable to, with slight changes, of course, to all of the astroparticle physics experiments in the world. Okay, so why does this not work? Do it this way? Nope. Like this? Nope. Yes, no. Okay, so what's the motivation for using machine learning in physics experiments, right? We're physicists, why should we want to do this? Okay, and there's an analogy that might hold for this, and that has to do with tools. I know you can consider having a task that you have to accomplish, like using the screw and putting it somewhere, putting it in some wood, putting it in the wall and sealing wherever you want. And there's a variety of tools that you might choose for that. You know, you can use a hammer, you can use a screwdriver, or you can use power tools. And my guess is that most of us will accomplish the task with any of these tools. But the point is that there's a difference in accuracy and speed. You know, probably the most accurate and fast solution is going to be power tools, but that comes with a caveat that you're going to have electric power. So, and then the same holds more or less true for machine learning in astroparticle physics. So we're using these things as tools to accomplish analysis tasks like physics analyses faster and more accurately, but we have to use them correctly, right? You can do a lot of things wrong when it comes to tools. You can easily imagine how to hurt yourself or others when using these tools. Well, with machine learning algorithms, you're probably not going to hurt yourself, but you can do a lot of things wrong. It's working now? Yes, okay. This is the outline of the talk. I will try to give you a very brief introduction to neutrinos, astroparticle physics, and IceCube. Since I learned that most of you are computer scientists, I assume that most of you are not familiar with this. And then I will try to go into 3 different analyses where we use machine learning and try to summarize the challenges and the solutions that we have applied and then show you the outcome of this. So this is the background rejection and the reconstruction of spectra. The search is for a very particular type of neutrino, the tau neutrino. And then, of course, we always have to have some deep learning, and deep learning for parameter reconstruction in IceCube has proven to work very well. This is the support of many people that at one way or another helped me put together this talk by providing me the slides or input of whatever kind. Okay, so what is astroparticle physics and why do we want to do this in the end? So we know since mostly more than 100 years that there are high energy charged particles coming from somewhere in the universe. We don't know where they're coming from because they are charged. And as they are charged, they are subject to bending by magnetic fields, which exist in the galaxy and out of the galaxy. And essentially when they arrive at Earth, like here in Argentina, for example, we can measure the energy pretty accurately, but we do not really know where they're coming from. That's very sad. We would like to know where these particles are coming from because they are so high energetic. They exceed in energy, they exceed what is possible with man-made accelerators like at the LHC by several orders of magnitude. Really, really high energies, the highest energy particles we've ever seen so far. So the best assumption we have that there has to be some sort of source that does accelerate these particles. And now we're looking for messenger particles that traverse the universe unhindered and also while retaining their direction information. And one candidate is gamma rays. These gamma rays, photons, light in the end of very high energy, does not get deflected by magnetic fields. So it does arrive at the Earth and you can then detect it with a Cherenkov telescope or with a satellite experiment. The caveat is the gamma rays can get absorbed, for example, in a dust layer or whatever. So that brings us to the third type of messenger particle, and that would be the neutrino. It's in a way the ideal messenger particle because it is electrically neutral, so it does not get deflected by magnetic fields, and has a very, very small interaction probability. But this small interaction probability is also a challenge because, you know, if something does not interact, very likely, and it's pretty hard to detect. So how you can circumvent this, I will tell you in a minute. So one more thing. If the physics that we assume here at Earth is halfway correct, then we assume the sources of high energy gamma rays, which we can see, also to be the source of high energy neutrinos that we measure, and the source of high energy cosmic rays. But we don't know yet. So that's sort of the spoiler. Okay, so what machine learning tools do we apply in astroparticle physics? There's mostly ensembles of decision trees, so good old random forests and Lucid decision trees that have proven themselves to be very reliable, very robust for several tasks. And there's, of course, different types of neural networks. Other things like support vector machines are not so often used. I've seen people try them sometimes, but in the end, they generally fall back to using neural networks or ensemble trees. Okay, now for the neutrino. So what is this? I mentioned this in the beginning, or like 2 slides ago. So the neutrino is part of the standard model of elementary particles. These elementary particles, they cannot be further subdivided. That's why they're elementary. And they come in what we call generations, right? And the neutrinos are the lightest. No, it doesn't extend here, that's a boson. So these ones here are the lightest particles. And the basic point for this kind of talk is that they can undergo reactions. Type of reaction is also not very important, but they can, in these interactions, they can transform themselves in what we call their leptonic partners. So you have an electron neutrino, and this electron neutrino can be transformed in an interaction with an electron. The muon neutrino can be transformed in a muon, and the tau neutrino can be transformed into a tau. And they do this with a very, very small probability only. So that's why it took so long to detect them finally. And okay, these are the neutrino telescopes of the world. There's several of them. There are, well, some of them under construction. IceCube, this is the one I'm going to talk about mostly. It's at the South Pole. Then there's one that's called KM3net that's in the Mediterranean. One of the older ones that's been upgraded lately is in Lake Baikal in Russia. And there's one that's under construction. It's called P1. It's going to be built right off the coast of Vancouver. So you might ask, why do we need so many of them? Well, they have a different sensitivity to different portions of the sky. That's essentially the thing. And of course, if you get funding, you can build more. Okay, now for IceCube. So IceCube is the thing at the geographic South Pole. You might wonder, why do we want to put such a large detector in such a harsh and remote environment? And the point is, as I mentioned, the neutrinos have a very small interaction probability. And there's 2 ways that you can circumvent that, get around this. First option is you can wait for a very long time to detect a sufficient number of neutrinos. Well, you want to get done with your analysis at a certain point. So the second option is a lot better. And the second option is you just instrument a large number of large volume, right? So this is what IceCube is. It's basically a 1 cubic kilometer large block of ice. And the details are a little more complicated. So we have these cables called strings. And on these strings, we have digital optical modules. I'll explain on the next slide how they work. And these strings, they are arranged in a triangular grid. And the strings have a interstring distance of approximately 125 meters. Say approximately, because this is the nominal distance due to issues when drilling in the ice and logistics. The distance is not always 125 meters. Sometimes it's 140, but 125 as a rule of thumb. And then there's what we call the main array. This is sort of what you can see here, right? This grayish area with the gray dots. And this extends from approximately 1.5 kilometers below the ice to 2.5 kilometers below the ice. So we're skipped the upper part of the ice. That has two reasons. First one is we can get rid of some of the background by putting it deeper. And the second reason is you need deep and clear ice. So the deeper the ice, the clearer it gets. Because when you have ice, then there's air bubbles frozen in it. And if you have more ice above, the pressure increases and you're basically pressing out the air bubbles. So ice down here has less air bubbles, less scattering. It's better ice, essentially. And then there is this yellow area, which we call ice cube deep core. Ice cube deep core also has these domes, also arranged on strings, but they are a little denser. So as you can see, the strings are a little closer together, and also the domes on a string are a little closer together. So it's 15 meters for the regular domes. It's only 7 meters for the deep core domes. And what this infill or upgrade array or whatever you want to call this does, it lowers the energy threshold. So we can detect neutrinos with ice cube up to or down to energies up to we don't have a threshold there. Down to energies of approximately 100 GeV. And for deep core, it's 10 GeV. So you lower the energy threshold by a factor of 10. For comparison, this is the Eiffel Tower. So this thing is really large. Okay. The way by which we detect this is Cherenkov radiation. And Cherenkov radiation is initiated when a charged particle traverses a medium with speed of light. Oh no, that says faster than the speed of light in a vacuum. That's impossible. I'm sorry. It needs to be. I discovered new physics. People should get me a Nobel Prize. No, that's a mistake. It should be faster than the speed of light in the medium, not in the vacuum. That's but essentially the speed of light that these particles traverse the ice is then close to the speed of light in the vacuum. That's the entire point. And then when a charged particle traverses in this medium, then you have a polarization of the medium, sort of little antennas, and these little antennas start to emit a characteristic radiation. And this radiation is called Cherenkov radiation. And you can actually see this when you look into nuclear reactors. So this is a picture of a nuclear reactor. They do glow, but they do not glow green. They glow bluish because of all the Cherenkov light. It's a lot of charged particles in water. Essentially, you look, in this case, you look in the cooling tank. This is not what this looks like in the ice, okay? They have a lot more charged particles in a nuclear reactor than we do, but to give you a feeling on what this light looks like. Okay, in our domes, we have a thing that is called a photomultiplier. Now how you want to multiply a photon. The basic idea is that you utilize the photo effect. So a charged particle, in this case, you have a scintillator before this, because this is the sort of the best and easiest picture I could find. We do not have a scintillator, but we have a photon coming out. This would be the photon, independent on how you produce this. And this would just, knock out a primary electron in a photocathode, right? And then you can focus this. And the entire idea is that you send this to stages of dinodes. And in each of these dinodes, you knock out more electrons. And in the end, after several dinodes, you have an entire cascade of electrons. So you have converted a single photon or a very small number of photons to a relatively large number of electrons. So basically, a photomultiplier converts a photonic signal to an electronic signal. An electronic signal you can read out with the readout electronics and do everything you want with that. Okay. And that's the fundamental unit of IceCube. That is the DOM. It's called the Digital Optical Module. It has one downward facing photomultiplier. So we're looking downward facing. It's north and south, always a little difficult. So downward facing means this thing looks towards the north. Okay, then you have something additional like high voltage supply, electronics for readout. Something that is very important are the flasher LEDs. So these are basically light sources that we have mounted on our DOMs, and we can just turn them on and off as we want in order to measure the properties of the ice. We have slightly better DOMs for deep core. That's not too important. The nice point about these DOMs is we have had very, very few DOM failures so far. A lot less than expected. And most of them actually happened during the deployment of the photomultipliers. So once they are in the ice, they're pretty stable, which is nice. Slightly larger fraction of DOMs have issues, but that is mostly in cases where the DOM next to the DOM with the issue has failed, so you can't really apply coincidence requirements. Okay, this is the IceCube collaboration. This can also be seen as an example for all of astroparticle physics, right? You can't do these things with efforts from a single university, so you have to team up across the globe, basically. And the light blue countries, these are the ones that participate in IceCube. We have a large participation from the US and from Europe, including Denmark, Sweden, Germany, and Switzerland, the Netherlands, and all other countries. Okay. The South Pole as a detection medium is not very nice. You know, I said that we press out the, not we, but nature did press out the air bubbles. That is nice, but nature can also be pretty mean. So this means our detection medium did form over tens of thousands of years, very long time. And that becomes problematic. For example, imagine, I don't know, 20,000 years ago, volcano broke out, scattered its ashes all over the world, including the South Pole. So here we are having to deal with these ashes. And that's actually something that we can see. I'm not really sure if this was a volcano, but we for sure see a large layer of dust right about in the center of our detector. This is the amount of absorption that can happen. It's the absorption length. No, it's not the length, it's the coefficient. And you can see that the absorption and also the scattering of the light actually varies with the depth in the detector. So this is not good, but we have to live with this. And you can also see that these larger peaks actually affect our data taking. So this COGZ, so center of gravity of the light that we've seen in the detector, is a function of the depth. And you can see the largest dip is at the point where we have the largest layer of dust. We have a bunch of smaller layers of dust, but you can see them as smaller wiggles actually. Okay. The good thing is our ice measurements have improved over time. We started out with actual ice core measurements. So people went to the South Pole, drilled ice cores and analyzed them in a lab with lasers, I guess. That was the very first ice model. It was not perfect. The other ones are not perfect as well. But we have replaced this by in situ measurements. So actually we flash these DOMs. So we turn them on. There's a light source inside the detector at a clearly defined position. And then we can go ahead and measure the light response or the electronic response by DOMs at certain positions, and then we can try to fit these scattering and absorption coefficients in order to obtain a better ice model. Okay, so this is in a way a summary on how the detection principle works, right? This light gray area is supposed to be the Cherenkov cone. The particle moving at the speed of light through the detector is supposed to be at the top, moving this way. And then each of these DOMs detects a certain amount of light. This light gets converted into a charge over time, right? Because of all the scattering and the absorption. Not all the Cherenkov photons, although they travel at a wavefront, are not detected at the same time. This is a washed out signal, right? This is time, this is charge. Okay, so when we put this to a somewhat higher level, what does this look like in the detector? We have 3 different kinds of events that I would like to mention. And the first one are cascades. A cascade is like, you can imagine that to be a ball of light in the detector. Maybe I should start with the color coding. So the color coding is the time. Every one of these little dots is one ice cube DOM that detected charge or light during an event. And the red DOMs did see light very early, and the blue ones very late, and then orange and green is somewhere in the middle. So you can actually see, and the size of the dot corresponds to the amount of charge that has been seen. So you can see that here in the middle, you have a relatively large amount of charge at relatively early times, and this moves then outwards. They originate from a special type of electron-neutrino interaction. It's called the charge current interaction, and a different kind of interaction, neutral current interaction of all neutrino flavors. It is preferable, I would say, that the interaction happens inside the instrumented volume. So the interaction that does produce the interaction of the neutrino that then produces the charged leptons that give us the cascade should ideally happen inside this 1 cubic kilometer of ice that we instrumented. There's some ways that you can circumvent this, can happen a little bit outside, but in that case, you would not see such a nice cascade. You would like see half a cascade or so, which is a lot harder to reconstruct. The angular resolution, so the question is, where did the neutrino come from? Cannot be answered very accurately, approximately 15 degrees. But I hope to convince you later that we can lower this by approximately a factor of 2 by using deep learning. The good thing is it has a relatively good energy resolution, right? All the light ends up inside the detector. All the light is collected by the photomultipliers, and we can relatively accurately reconstruct the energy of the neutrino. The other one are track-like events. They originate from muon neutrino charge current interactions. In these charge current interactions, the muon neutrino interacts, produces the muon. And in this case, you can see that the muon moved this way through the detector, right? Again, red is early and blue is late, and it started somewhere here and moved this way. In this case, the interaction may actually happen outside of the instrumented volume. So a muon can traverse relatively large amounts of ice without being fully absorbed or running out of energy. It will lose energy on its way here, but depending on how much energy it had in the beginning, it might survive. They have a good angular resolution, right? There's a long lever arm that's available for reconstruction, so you can actually see this and reconstruct the direction very good. The point is that the angular energy resolution is relatively poor. And that's because of what I just said, right? The muon can be produced somewhere out the detector. We do not know where. Then it travels towards the detector. We'll lose all kinds of energy. We do not know where it came from. We do not know how much energy it lost. And that is actually one of the larger challenges in the analysis. Something that's pretty special are double cascade events. These double cascade events are a series of 2 cascades that are connected by a track. And these double cascade events solely originate from the interaction of a tau neutrino. So this tau neutrino interacts with the nucleus, a tau lepton is created, and this tau lepton actually decays at a second vertex, and then again decays in the W minus, that's a boson, and another tau neutrino. So it's like this Dumbo shaped events, right? You have a cascade, you have a track, and a second cascade. Very unique. But the point is, so if we would have seen this at one point, clear identification of a tau. Unfortunately, the tau track is relatively short. It's only about 50 meters per PV. So PV is approximately, well, it's not the highest energy that we've seen, but it's close to the edge. So not very likely that we will see this. Okay. Any questions so far? that I wanted to say in the beginning, but I didn't. If you have any questions, I'm going too fast. Anything remains unclear, just stop me right on the spot. Okay. Sorry. How often does what happen? Any of these events? So track-like events happen several hundred a day. Several tens for Cascades. And taus, I don't really know. Couple per year. So the reason for the differences in number is that you can have the electron neutrinos and the mu neutrinos be produced in the Earth atmosphere. I'll show that later. But the tau neutrinos have to come from astrophysical sources. So you produce a relatively large number. I'm saying relatively large. You produce a large number of neutrinos in the Earth atmosphere, but these are only these two types. The expectation is that we also produce neutrinos in astrophysical sources, but then, of course, because they emit towards a larger angle and at a small spot of the angle sits the Earth, you see a lot less of them. Okay. Now, in order to do some machine learning at some point, we might have to extract some features. Might be a good idea. Okay. So I divided them into 3 categories. You can come up with different categories, it's fine, but these are the 3 that I like to use. The first one are really, really simple features, and they do not require anyone to be sophisticated or smart or anything else, right? For example, you can just sum up the total charge that all of the photomultipliers did see in the event. Relatively straightforward. Then you can start like counting all of the DOMs that did participate, all of the strings that did participate. You can just basically count anything, okay? Then you can go ahead and have some simple fits. This example assumes that we have a track-like event, right? You assume this muon to travel on a straight line, and then you can just go ahead and minimize a chi-square according to some track hypothesis. Also not too difficult. And the third one are likelihood-based reconstructions, where you basically have a certain set of parameters, and you're just trying to minimize the likelihood so that they best describe what you've seen. So the pattern of light, essentially. Okay. Now I'm running or getting towards one of the example analysis, and that is the reconstruction of neutrino energy spectrum. So what is the actual analysis tasks? So this is energy in physicist units, it's GeV. And this is the flux, but the flux got multiplied by energy squared to basically make some of these features more visible. Okay. And well, the red line is the most important one. That is the sum of all the other components. And there are several theoretical models that predict something, how this flux should look like. And then the task of the analyzer is to just find some data points to put somewhere here and to actually measure something and then constrain models and so on. Okay, so where do all of these neutrinos come from? Well, there's the green line. That would be an astrophysical neutrino. That in this case would not be detected because it was in coincidence with the cosmic ray, but for the sake of argument, let's assume we can. And we're assuming that this astrophysical neutrino will follow a power law. So the flux will fall off as the energy squared. Then there's all the atmospheric neutrinos that contribute to that. So they are produced in the cosmic ray interactions, right? These are the protons, for example, that I mentioned in the very beginning. These protons come in at very high energies. They hit a nucleus in the Earth atmosphere. And then a lot of stuff happens. We skip this stuff and just jump right to the particles that contribute here. And these are mesons mainly. Mesons are particles that are made of 2 quarks. And the important ones are pions and kaons. So in the pions and kaons, they decay into muons and neutrinos. And the neutrinos that originate from pions and kaons, this is what we call conventional atmospheric neutrinos. And they fall off differently in energy. So it's e to the minus 3.7. And the reason for that is that these mesons, they live relatively long. So they have lifetimes on the order of 10 to the minus 8 seconds. So for a particle, 10 to the minus 8 seconds is a long life. And during their long life, they can lose energy in collisions, whatever. And that means they do have a different energy dependence than the initial cosmic ray. And the conventional component is well known. We measure it all the time. So the prompt component is originating from mesons that also have a charm quark, and they decay much faster, these mesons, right? They live on the order of 10 to the minus 12 seconds, so 4 orders of magnitude smaller in lifetime than the pions and kaons. And because they decay so swiftly, they do not have any time to interact and do stuff. So they follow the spectrum of the initial cosmic rays more closely, and we expect a different energy dependence. And now if I go back, you can see this here, right? This is the e to the minus, it's not exactly e to the minus 2, it's e to the minus 2.2 in this plot. So this behaves differently. And then you have the prompt component that we have not seen so far, but expect to be there, behaves somewhat differently, larger flux for the conventional component. And then as a sum, you see a flattening towards higher energies. And this flattening can then be interpreted as, no longer conventional atmospheric neutrinos, because the flux is so small at these energies. So this has to be astrophysical neutrinos, for example. Okay, well, all the good in the world comes with a caveat. And these are atmospheric muons. These atmospheric muons, they are produced in the same processes as the neutrinos I'm actually looking for. But the point is that atmospheric neutrinos are 10 to the 3 times more abundant compared to atmospheric neutrinos. Depends a bit at what level of analysis you look, but that's sort of the ballpark number, right? So, and their signatures in the detector look more or less the same, right? The neutrino does not carry a little flag that says I was induced by a neutrino or I'm an atmospheric muon. So we have to sort of get rid of those. The good thing is that you can use the Earth to shield the muons. Neutrinos, due to their small interaction cross-section, they can traverse the Earth. Muons cannot. So the easiest and first thing to do is we sort of look upwards. In the case of a neutrino telescope at the South Pole, means we look north, or in angles. This means we look at angles larger than 90 degrees. 90 degrees would be the horizon. You can place the cut slightly towards 86 or so. This has to do with the fact that if you look at an angle of 86 degrees, it's slightly above the horizon. So you increase your sensitivity for the neutrinos, but all the high energy muons are very likely to just range out. So you're not going to see any muons anymore. The problem is a bit that because you do some reconstructions and then you can just look at the angle, what came from where. And for some cases, you will just falsely reconstruct the muon as upward going, although it must have been downward going because it's physically impossible to be downward going. Okay. And the point is that the number of atmospheric muons is so large that there's still a really significant fraction of downward going muons that we reconstruct as upward going. And so this is basically the situation we end up with, right? The red ones are atmospheric muons, falsely reconstructed. So this is the reconstructed zenith angle, not the true one. And these are the atmospheric neutrinos. And as you can imagine, this background is significantly harder to reject. Cannot just apply a cut. Okay, so that's the general background rejection strategy that we use. And that is more or less true for a lot of experiments in astroparticle physics, right? So after all of our reconstructions of features, we end up with a really, really large number of features. It's approximately 1,200, but you can try and use all of them, but I'll try to convince you that this is not the best idea. Then we train a classifier, but as you will see later, training this classifier and evaluating this is not enough. We need to place an additional cut on the classifier. Okay, so how can we achieve a well enough feature selection. This is actually one of the more critical parts of the analysis. So initially, you start up with something on the order of 1,200. Okay. Then we go ahead and blacklist stuff. You would just everything that's, for example, only present in Monte Carlo simulations. You don't want to train anything on your Monte Carlo truth. That's kind of straightforward. You just blacklist that. Anything that might give you a certain bias for something, that's also something that you would exclude and blacklist. Get rid of about 100 features. Apparently, a lot of our features are constants for some reason. This, for example, might, if there's something constant, this might, for example, just encode that a certain algorithm has failed in reconstructing this. One can then go ahead and start debating if an algorithm in reconstruction ultimately failed. Can I use this somehow? But if it's constant all over, then it's useless. You can just get rid of this. We also have a lot of correlations in our attributes. You can imagine. So one example is, just going to flip, it's the zenith angle. We reconstruct zenith angles and reconstruct and directions basically from all our reconstruction algorithms. So imagine you have 10 reconstruction algorithms, you reconstruct 10 zenith angles. These zenith angles might differ, but they might also be highly correlated, right? So there's not enough gain, I want to say, in using 10 different zenith angles in the training of the machine learning classifier. So this actually gives the largest decrease, right? You go from 800 to 300. Then we have to check whether our data and the simulation that we use for the training, we do not have annotated historical events, so we have to rely on simulations. If all of this is good enough simulated to be used in a classifier, and then we use something that's called MRMR, so minimum redundancy, maximum relevance. And in case you do not know this, MRMR basically just selects features according to relevance and redundancy. So you compute the relevance towards the target class, and then in the first step, and select the variable that has the highest relevance for this classification task. And then in the later steps, you only add variables that give you sort of a trade-off between the relevance for the target class and the redundancy with all the features that you have already selected. Okay. And in the end, you end up with something like 60. 60 is okay. 60 you can use. Why not something else? Why not use a forward selection or backward elimination? Well, first of all, it takes a long time to do that. And it also, we found that it's not really stable, right? You can have these indices, Jacquard and Kucherva's index, that you can use for the, basically to check if you're selecting more or less the same variables all over the place. And you can see that for MRMR, this increases steadily, as you increase the number of attributes, this becomes more and more stable, and the forward selection becomes less and less stable. Okay. The detection of data and Monte Carlo mismatches. This is a difficult thing, right? As I said, we do not have any historical examples that we can use for the classification or as examples for training. So everything we do fully relies on that we correctly simulate the detector and all the electronics. And as you can imagine, this detector is a complicated thing. A lot can go wrong. And there's two examples here. We can probably agree that this has a sufficient agreement. And here we can probably agree that this has an insufficient agreement. Blue is simulation and orange would be the observations. But there's a lot of cases where it's somewhere in between, Maybe this is statistics, maybe not. So, well, first of all, we're only looking at one-dimensional distributions. So anything that has to do with correlations gets ignored. And then if you decide on comparing this, and you have to ask yourself, which metric are you going to use? And more importantly, metrics are available. That's not really the problem. Which threshold should I use, right? I mean, if the discrepancies are like here, if this would be simulated well here, and then here at the higher tails, is this statistics? Is it not? It's very hard to tell. So one can ask a different question. And then the question is, how much will the classifier that I'm trying to use be affected by these mismatches? And the general idea is pretty simple. And this is, you just train your classifier to distinguish between simulated and experimental data. If my simulations are perfect, then this is impossible for the classifier to achieve. Well, as you have seen, our simulations are not perfect. So once I run this, I can then sort the features according to their importance, and I can go ahead and discard the top end features. And then this has the advantage that I can exclude the mismatches to an extent where the classifier is affected by this, right? I can then say my classifier does not care about this anymore. It's not affected. Okay. So on the top left, you see area under curve. The blue line is there have 0 features been removed. And then the red line is 12. And orange and green, it's 4 and 8. And you can see, well, the gray line might be hard to see, but it's like the 0.5, right? Just separating this. This is random guessing. And if we actually go ahead and remove 12 of these features, then we get pretty close to random guessing, coming from, well, 0.67. And also the prediction score, if this was a classification task that one might try to achieve, then is already pretty bad, right? But you can see that it can get even worse. And again, the color coding is the same. If we exclude 12 of these features, then this is well centered around 0.5. If 0 features are removed, then there's a bunch of events that end up here, which would be actually pretty well classified. Okay, now we go to the classifier training. This is where we use random forests. In our project here in the CRC, others use boosted decision trees, which is fine, right? Important point is this is the main output of a random forest. So we classify all of the events by every tree, and it's a binary classification. So either a 0 or a 1, 0 being a background muon, and 1 being a neutrino-induced muon, and then this gets averaged over the number of trees. Okay, this is just again motivating what the signal in the background is. This slide should have come before, right? Background are muon tracks falsely reconstructed as upward going, and signal is muon tracks correctly reconstructed as upward going. And if they're correctly reconstructed as upward going, then they will have to be induced by a neutrino. Okay, so this is the classifier output. You should pay attention to this one first. And you can see, well, there's a large peak at 0, so a large number of background muons that are correctly identified as those. Also a large number of neutrinos correctly identified. And most importantly, data given in black and simulations as the yellowish data points, they agree. So it's not like in data and simulations, in either of them, suddenly there's a large peak somewhere in the middle or something strange happening. So that's good. Up here, you have a number of possible other background sources that I did not mention because they're not overly important, as you can see, right? Red is atmospheric muons falling off as classification score, and green atmospheric muons rising. It's a function of classification score, and the rest is more or less constant, right? It's other new mu interactions and neutral current interaction of other neutrino types, but they're really, and that's the important message, they're really subdominant compared to the other ones. But you can also see if you just trust the default classification of the classifier, and that would generally apply a cut here at 0.5, then this is not sufficient because at this point, we're still very much dominated by the background. Okay, so this requires an extra cut. And well, it then somewhat depends on where you want to place the cut. So we have run this analysis in different configurations of the detector. I should have mentioned this at the beginning. I'm just going to repeat it now. So IceCube was built at several stages because it's at the South Pole. You can't work in winter. It's dark. It's cold. Everything's going to freeze. So it was set up in multitudes of strings, right? So 59 strings was a one detector configuration, 59 strings was one, and then we finally ended up having the full detector. 59 strings, they made us choose the cut, or not, they didn't make us, I chose it, to be at 0.1, and there's also sort of a historical development that you can see here. So these are plots from the original paper, and when we published this with IceCube 59, no one trusted us that the reader would understand what the classification score would be for some reason. And so they decided that the x-axis should read number of trees, a number of, it's not even complete because it should read number of trees that voted for this event to be a neutrino. But okay, 2 years later, not a problem, and we could go with confidences. So, and we did some improvements on the analysis between here and here that had mainly to do with some feature engineering. And we ended up having 200 neutrino candidates per day for IceCube 79. And we had 80 for IceCube 59. And for both analyses, we have a relatively high purity. So we're expecting less than 0.5% of the events to be atmospheric muons. One could argue that, of course, when the detector gets bigger, you will, of course, detect more neutrinos. But even if you correct for the effect of the growing detector, then there's still an increase between here and here. Okay. Then it was realized that, of course, you can do more than just cut in one dimension. You can cut in 2 dimensions. That is because the classifier output is energy and zenith dependent. So, and if we take this into account as well, then we can optimize the classification score as a function of energy for 2 different zenith bands. And they look slightly different, right? It's no longer a straight cut. It's a lot more sophisticated. And we end up having 300 neutrino candidates per day. So this is really good. This is likely as good as we can get, but maybe someone can prove me wrong. Okay. Then in order to actually obtain these data points around the spectra that I mentioned in the beginning, we have to actually go ahead and reconstruct the spectrum. This is in principle straightforward, right? You have a measure of your energy and then you just spin this. Okay, it's not that simple. And it's not that simple because it's an inverse problem. So as I said, we detect the neutrinos indirectly, right? We do not see the neutrino. We only see the muon that, or other leptonic partner that emerges from it. And well, we also do not actually really see the energy of the muon. We also have to take an approximation of that, right? So some energy proxy for the energy of the muon. And so this is basically the equation that describes this. So we're measuring the energy spectrum of the muon indirectly via some muon energy proxy. And then you have this integral equation where this is the neutrino energy spectrum, number of neutrinos per energy bin essentially. And then you have this term here that captures the physics of the neutrino interaction. So it basically describes the probability of having a muon of energy E mu be produced in an interaction from a neutrino with energy E mu. So, and this is why this is complicated, right? This is the smearing that we have. So this is the true neutrino energy, and right. So the smearing is on half an order. Okay, how do we do this? Well, there's a bunch of algorithms that can help you do this, and I recommend a lecture on inverse problems and their solution by Michael Schmeling on Wednesday, 9 a.m. Basic point is that we apply. Well, first of all, we're not just having the physics of the neutrino interaction here, but replace this with the response function A. And this response function A basically captures And we have a sought after neutrino spectrum right here as F. And then you can apply likelihood, for example. Okay, and then these are some results, not just IceCube. For example, you have this IceCube parameter fit. It's basically a forward version of what I just said. And then one of the analyses that I was showing was IceCube 59. This is here. It's not yet perfect, but IceCube in the 79 configuration was then able to actually see this flattening of the flux right here. So basically, we did see what we would expect. And there is also Antares, which is another neutrino telescope, also in the Mediterranean, that I did not have on my first slide. These are the red dots. So everything is more or less compatible with each other, but that has also to do with the fact that we have relatively large systematic uncertainties, right? And these large systematic uncertainties have to do with the effect that we have a still limited understanding of the ice, actually. Okay, how am I doing on time? Good. Okay. So another thing that I would like to show you are seasonal variations of atmospheric neutrinos. And as I said, atmospheric neutrinos, they originate, if we're concentrating on the conventional component, then they originate from the decay of pions and kaons. And these pions and kaons, as I said, lose energy, but they do lose energy differently compared to the season. And we also see differences in the rate of atmospheric, I think this is muons, atmospheric muons. And as such, we would also expect this for atmospheric neutrinos. This has to do with the temperature of the Earth atmosphere. And you know, when the temperature changes, the density of the medium changes, and the physics of the interaction somewhat changes. And this is just from 2007 to 2009, and you can see this is the temperature changes for different pressures, and this is the observed amount of atmospheric muons in IceCube. And you can see that this does follow a nice curve, right, with the seasons. But and we see the very same thing actually also for neutrinos. But what we'd like to see is actually the effect on the spectrum. And the effect on the spectrum is actually tiny, and you can see, tiny but small. And you can see that is also various energy. So IceCube can start to measure approximately right here. And you can see, well, for the season June to August, so summer basically, we expect a smaller flux also, and decreasing with energy. And December to February, we expect an increasing flux. And the question is, can we measure this effect with IceCube? And we're trying to do this, and we're trying to do this with machine learning also. And the idea is to have a machine learning based reconstruction algorithm. And instead of reconstructing the particle spectrum by likelihood, one can go ahead and this is just a toy example. We have all of these bins, and you can do, well, might go ahead and interpret this as a multi-class classification problem. And then you can have some machine learning algorithm in the middle, and then you can have the estimation of the spectrum. Well, it's not that simple, really. And the point is why this is not that simple is these are selected examples, basically. And you can see that this is the energy, and this is the confidence. And you can see that the confidences, the maxima and the confidence on which the classifier would base its decision, they're not very distinct. These are actually pretty good examples. You can have some where it's basically almost the same, right? Okay, so we run this iteratively, we discretize, we train the model, we apply the model, we reconstruct the spectrum, and then we update the weights according to the unfolding results. You can actually do a lot better. And this is largely the work of Mikko Bunzo, and you can get the software right here. And then you can have a variable step width, right? In your iteration, you basically optimize the step width, and there's several optimizations available. And you find an optimal alpha via this equation. And what this did solve is actually, you can see this here, this was the original DC. You would just end up in a minimum and then go up again. But with this variable step size, this nicely converges for most cases, which is really nice. Okay, and these are some of the very preliminary results. And you can see, well, first of all, this says IceCube work in progress. We're not done yet. And you can also see that this is only based on 10% of the data. This is why this is still work in progress. But we hope to have the full data set very soon. And you can see that this is very hard to distinguish just based on the spectra alone. Again, this is because we have large systematic uncertainties. But if you actually look at the ratio to the yearly average, then the idea is that the systematic uncertainties of the detector, they do not care about what season it is, right? So if you look at this, then you can see some discrepancies here, right? This is season December to February and June to August. So summer and winter, basically. Definition of summer and winter, which is what sort of depends on if you're in the north or in the south, but you can see discrepancies, right? And for just taking half-year averages like January to June and July to December, then this sort of averages out and you see almost a straight line as you would expect this. So this is very promising. And actually the first application of this algorithm in IceCube, and we hope this to be out very soon. Okay. Next thing I would like to talk about is double cascades in IceCube, the new tau injection, if you remember this. And as I said, the tau track is very hard to see. This is not easy, not straightforward. And that is because the tau needs a relatively large, right? You have a 50-meter tau track per PeV in energy, and you have a string-to-string distance of 125 meters. So the least thing you would have to expect is that it can travel from one string to another. 2, maybe 3 strings would be even better. And then you have to multiply this even more. So probably 4 or 5 PeVs what you would need. And this is just very unlikely. It's not impossible, but just very unlikely. So instead, we're not looking for single and double cascades, but you can look for single and double pulses. For a single cascade, for example, as an electron neutrino would induce it, you have a single cascade seen by a single photomultiplier as a waveform like this. A double cascade, on the other hand, pretty much independent of the energy of the tau, you have one cascade, tau traveling, second cascade, and this would look something like this. So sort of reformulate the analysis task to look for pulses that look something like this. Okay. And this you can also do by machine learning, of course. And then in this case, we have 2 random forests, where the first random forest is only trained to reject single cascades, right? This is the single cascades, it's in orange, and the double cascades are in blue. Second y-axis gives you the purity, and we can apply a relatively weak score cut at 0.2, and then proceed to the second random forest, where you would again try to reject the atmospheric muons that also come in all other types of background. And if one does that, and in this case, the score cut is optimized somewhat differently, we have 2 surviving events. This one has a double pulse score of 0.565, so it's a very likely background, and you only have like one DOM exhibiting this double pulse waveform. But this one is very likely induced by a new tau event, and here you can see this is 3 DOMs basically. Well, the orange one is clearly the one that exhibits the most double pulse-like structure. The green one, a little less, and the blue even less. But this is very likely been a new tau event. Okay. Okay. Now for neural networks and reconstruction in IceCube and why we apply this. Well, everybody does. So why not try this in IceCube? But there are some somewhat better reasons. Okay. So if we can improve our reconstruction methods, then this will lead to an increased sensitivity for the detection of the neutrino sources. There are several hardware limitations that apply at the South Pole. You can imagine you cannot have an arbitrarily large computing farm at the South Pole. A lot of our information has to be sent by satellite. So there's bandwidth constraints that apply. And what's also important, we need to process the events in a given time frame to prevent an event pileup. And these limitations call for robust methods, and they should ideally be able to handle raw data and to do that in a constant amount of time. Neural networks are computationally inexpensive once the network is trained, because they perform a fixed amount of operations, and the runtime is then largely independent of the input. And well, they exhibit translational invariance. So the position of the cat, if you're trying to classify a cat, does not impact that an image was classified as a cat. And we try to exploit this in a way by saying that the physics of the neutrino interaction is invariant in time and space. So the first point where this was applied are cascade reconstructions. Why cascades, you can ask? Well, we have a missing lever arm due to the spherical light distribution, compared to tracks, where, for example, the ice properties can average out over the path that the muon takes through the detector. They're local and therefore more susceptible to the ice properties. And our quantities of interest are then the deposited energy and the direction of the incoming neutrino. So why cascades? Approximately 2/3 of ice cubes high energy starting events, which is a special kind of event, that are very likely of astrophysical origin, are cascades, right? And the directional information is awful, right? 15 degrees. If you look at the sky, 15 degrees is huge. As for comparison, if you look at don't look at the sun, look at the moon. They're both approximately the same size, just for safety reasons. They're about 1 degree in diameter. So you can hide a lot of astrophysical sources in 1 degree already. So imagine what you can hide in 15. Okay. So, but there are some differences between images and ice cube. Images are generally rectangular. Ice cube has a hexagonal grid and also has these subarrays, right? And ice cube has a high dimensionality and variability. But we'll tackle that. So the input dimensions basically are transformed in a way that we first take the infill arrays like upper deep core and lower deep core, and we just straighten this out. All right. Then you have 8 deep core strings times 10 DOMs times how many input features you will select. The lower deep core, 8 strings times 50 DOMs times n. And the main array, this is basically just transformed into a rectangular image by zero padding, right? So we just keep the information on the blue ones and rectangularize it. I don't know if that's a word, by setting the edges to 0. Right, and then the input dimensions become 10 by 10. 10 by 10, that's the dimension of this, times 60 is the number of DOMs, times n, number of features that you would like to select. Okay, so what features can we select as input? This is not straightforward. We can obviously, for computing reasons, not use the full waveform. This is a bit tricky, gets simply too large. But this waveform can then be discretized. This discretization is what happens with these grayish lines. These are then pulses, and then from these pulses you can go ahead and derive some features. I hope I remember all of them. Okay, you can of course, time is on the y-axis. You can just take the time for the mean, right, of these pulses and the standard deviation. You can take the relative time of the first pulse. You can also take the relative time of the last pulse. That's here. Then you can also look at the charge. You can, of course, take the total charge, and then you can take the charge after 100 nanoseconds and the charge after 50 nanoseconds. And you can take the 20 percentile of the time, the time at which 20% of the charge has been collected and the time at which 50% of the charge has been collected. So these are the input features. What we also use are hexagonal kernels. They are in a way transformed in a similar way as the ice cube array, right? You just start with this, then you might have 0 padding, and then just shift this to make this rectangular. Okay, this is what the network architecture looks like. 20 hexagonal convolutional layers for the main array, then 1 flattened layer, 8 convolutional layers for upper deep core, 14 for the lower deep core, and then you have 2 subnetworks. This upper network then estimates the energy direction in X, Y, and Z, and then this direction X, Y, and Z can be combined to reconstruct azimuth and zenith. These are the predictions, but we're also interested in the uncertainties. So why are we interested in the uncertainty? I should probably explain this. IceCube sends out alerts to other telescopes. So in case we see a high energy neutrino, we say, hey, we did see something and we saw it at this and that direction, and we have these and these uncertainties associated with that. And these uncertainties are important for other telescopes to know how much they can trust or estimate. So it's not just about estimating azimuth and zenith, it's also about estimating the energy, the uncertainty associated with that. Okay. Regularization happens via dropout in these neural networks, but we gradually decrease this dropout at later layers. This can be done. We really have a huge amount of training examples. It goes into the millions, actually. What's more important is that we actually drop individual DOMs during training. And we try to do this in order to have an increased stability, because if you train your network on like the detector in the configuration that we have now, and then I don't know, tomorrow 10 random drops because of aging or whatever, they just fail. And then you have to go back and do all the work again. So, but if we train a network where we, in the training process already randomly drop at certain points some of the DOMs, then we expect this to be more stable. Okay. So what are the results? The results are, of course, good. It's always the comparison here between the likelihood estimation, right? Where you can see this is in terms of deposited energy, not okay. This is the energy scale in any case, and you can see that although the likelihood reconstruction does relatively well for the low energy, it just spreads out in the end, right? It's not, if you would have looked at the mean and the standard deviation, this is not too bad, but you have a relatively large amount of events that end up clearly falsely reconstructed. And if you let a neural network do this, then these fuzzy tails, so to say, up here, they just go away. So this is the residual actually, and then you can see that, well, it gets really bad towards higher energies, whereas the neural net is pretty stable across all energy ranges, which is good. On the right-hand side, you have the runtime per event. So this is the standard reconstruction. And you can see that the standard reconstruction really largely depends on the input that you have. So you can imagine for, if you run this likelihood minimization for high energy events where you have a lot of information in a lot of DOMs, then this takes longer to run. Obviously somewhat faster for events with less information. But then if you apply the neural network, then there are also some dependencies on that. The bottleneck is mainly then condensing, extracting all the features that I mentioned in the beginning, like the timing information and stuff, right? So, but it's a lot less dependent on the input than the standard reconstruction, right? So it doesn't take very long to run. So this is a log scale, obviously. So this leaves directional reconstruction, and the important lines I'd like to point to are the standard reconstruction 50 percentile. So this is the opening angle between the true and the reconstructed angles. And you can see 20%, 50% lie below here for the standard reconstruction, and solid lines 50% in blue then for the CNN. You can see that the CNN is not as good for smaller energies, but actually starts beating it by approximately a factor of 2 around here. But but although it's not much better here for low energies, this is not bad, because the energies where I actually expect astrophysical neutrinos to be dominant, it starts right here, somewhere here, right? And then actually increases as the energy increases. Okay, this already brings me to the summary. So I hope that I could show you that we can use machine learning at different points in different analyses in astroparticle physics, that we can use it for reconstruction of background, that we can use it to actually distinguish and finally exclude badly simulated features, that we can use it for classification, already had that, that we can use it for the reconstruction of energy and directional reconstructions and things like that. And also for spectral reconstruction, but that's a whole different topic. Thanks.
Yeah, thank you very much for this interesting and informational talk. Are there any questions from the audience or from the Zoom? Yeah.
Thank you. So my question is actually the following one. So you, if I got that correctly, you mentioned that you're labeling the data through simulations. So have actually simulations that are taking the data from the experiment and then they're labeling the data, and then you're fitting that to the classifier. Is that correct?
I'm not sure I understand the question. Can you maybe take down the?
Yeah. Okay.
Thanks.
No problem. So if I got that correctly, you mentioned that you are running a simulation on top of the data that you collected in order to perform a classification task, right?
Yes.
So my question is then, is this kind of simulation prone to error itself? Because I'm assuming, given that you are collecting the data, real data, then you have also confidence intervals associated to the detection of the event. And then also that error should be considered while doing the inference task. So my question is how this interval of confidence is then affecting potentially the classification, and how the robustness of the classification could overcome potential errors. Thank you.
You're referring to these confidence intervals, or in general? I mean,
in general,
okay.
Actually
from the very beginning
itself.
Yeah.
So given that you have data, thank you. Given that you have data that you are simulating, but the data is actually sampled from the real data, and the real data you have actually a sensor, and so you have an interval of confidence having an error, and therefore even when you are training you have that interval of error, and so if that goes out of the boundaries could have a misclassification at the simulator time. So it's actually the pre-processing step where you're calculating the data and then labeling it.
Okay, I'll try to answer what I understood. So of course we have to check our simulations, right? This was not in this talk, but this is also a huge step for every experiment that is built, not just in astroparticle physics, right? What you can do, for example, if you're lucky enough to have a calibration beam, like when you're at CERN, when you can more or less control your experiments, you run a calibration beam that has a very precise, in terms of how precise you can actually tune it, very precise energy, for example, and then you can go ahead and do this. This is sort of what we do with the light sources, right? Where we very precisely know where the vertex, where the origin of the light is. And then you can do the fits. So in astroparticle physics, it's not that simple. We do not have a calibration beam. But what we can use for calibration, for example, are atmospheric muons, because they're really abundant, right? And then you have physics theories behind that tell you, well, this should be the interaction probability, and you can, for example, take interaction probabilities from CERN and measurements. Then sometimes you have to extrapolate because we're going to so large energies, and it becomes all kinds of complicated. And this is prone to all kinds of errors, right? But in the end, you will have to compare your simulations to your data, and if that does not match, and you have to go one or two steps back and then actually try to find out where the error is. Maybe it's just a coding error, then this is easy to fix. Maybe we didn't understand the physics correctly. This gets harder then, right? And then well, simulating it's horrible. I'm glad I don't have to do it.
Thank you very much.
Okay, do we have further questions?
Not a question, but maybe a clarification for your question. It is not that the simulation is labeling the data that you already have, but it is mimicking what is happening in the real world, which is first you have a particle with properties like energy, and then you have the observation coming from that particle. So you cannot label what you have in the data, but you have you have it exactly the other way around. You produce feature vectors for labels that you choose. The label is the input of the simulation, which makes everything worse. Because now you can have for one label you have many different possible outcomes, and these outcomes overlap heavily. So for each feature vector, multiple energies might be probable. Yes.
Anything in the chat? Okay. Okay, probably I have a question. Since ice cube experiment is not my main topic, I also might ask something. So you were talking about the background that you have, which you said like you have on the one hand the signal, the perfectly fine classified or reconstructed event. Muon event. Yeah.
Which one, muons?
Yeah, it was around about 30, slide 30 or something. Yeah, exactly. Yeah, okay. And the background, which is the falsely reconstructed event. Is there anything more? I was just wondering because it sounds like, oh, we just have two types of particles, and isn't there so much else that you can?
Yeah, there's more. This is a simplified version of this, but as you can see here, right? So there's of course more background. It's a 24/7 4-pi detector, so IceCube sees everything, much like Sanda. But these are the most important types of particles. I mean, right? You have the atmospheric muons because they're everywhere and they're so abundant. This is of course the largest background, and of course because they mimic the signal that we actually want to see. And then there's the signal class, and these other colored lines are other signals that we also might see. This is simulation, so this is where you would expect the new tau to be, right? They also come in. We can't probably distinguish that. If the tau event looks bad enough, it might mimic a muon track. But it's really subdominant, right? It's like how many orders? It's like almost 7 orders of magnitude below the muonic background. New cascades. So these cascades and tracks, they are not always as clear and nice as I was showing them. So these are, if you go to like really high energies, this is what I was showing, then they become clear and nicely distinguishable by eye. If you go to lower energies, then it might be, you know, a track that just hits the detector somewhere at the corner. Well, this could be a track, this could be also a cascade, and this also then becomes by eye very hard to distinguish. So also the electron neutrinos, for example, they contribute to this, because if it's just somehow strange inside the detector, then it might very well mimic a track somehow, or the track hypothesis might somehow be reconstructed to this. But this is then, I don't know, what's this, 4 or 5 or at least 5 orders of magnitude below this. And then New mu apps. This is probably a new mu neutral current event. So this is basically all cascade events, right? Everything that makes a cascade. If the energy is small enough, which it will be, because power law, might in a way also look a bit like a track and fit to the track hypothesis. So yes, they are also there, and they should be considered, but they're also not abundant enough to give them too much attention, right? As is done in this plot, it's very reasonable to check, I don't know, to not have like a tau peak somewhere in the middle or so. Just check this for reasonable behavior. This would be my recommendation, but they're not going to be. They're going to be in the sample, of course, right? But again, 4 or 5 orders of magnitude below this. So if you consider having 300 neutrino events or neutrino candidates per day, if you're 4 orders of magnitude below this, then there's one of the other per day. So that's an amount of background that we can live with.
Okay. Thank you very much.